Today we start a new chapter. Chapter 27. Magnetic field and magnetic forces. Magnets are weird, right? They are magical. Do you know Richard Feynman? Who doesn't? Everybody else knows Richard Feynman, right? You also don't.
I don't know.
You don't?
I don't know.
You don't know. So you write Richard Feynman magnets on YouTube and watch this 7 minutes. The interviewer asks, like, why magnets repel, okay? And his answer, long story in short, his answer is that magnets just repel. It's very fundamental, it's very basic. I can't describe that in terms of something else. For example, he says, I can't tell you that it's like they are connected by rubber bands and that's why they are repelling or attracting, because to describe the repelling and attraction of rubber bands, I have to use magnetism. You see? So that's what we are doing in general. Like, we are looking at very fundamental properties of electricity and magnetism, and now we are on the other side of the coin. But it's one coin, okay? So let's remember magnets. The name magnet comes from Magnesia, a place where they have found it 2500 BC, okay? And do you know the name today? Manisa, yes. Good. Okay. So we describe magnets as having north pole and south pole. It's very similar to having plus and minus, but it's also very fundamentally different. So if you have north facing south, then they will attract each other, right? And if you have this arrangement, NS, NS, then they will repel each other, right? Also, if it's, let's just for completeness also plot this one, they will repel too, right? There are also certain kinds of materials that are attracted to magnets, right? Like a nail made out of iron maybe gets attracted to magnets. And what's really happening here is that the material itself, okay, let me first start with this material. Let's zoom into this material. If I zoom into this, it's actually made out of NS, 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 infinite number of N and S, all more or less aligned, right? So that's a ferromagnet. Everybody signed the attendance? Can you please take it? All right. NS aligned, and they create this NS macroscopically from this alignment. This one is paramagnet. So it also has N and S. This one also has N and S, but they are not aligned. Okay? But once they see the magnetic field, they get aligned. And that's why, how do they get aligned? Basically, N attracts S, or S attracts N. That's how it becomes N over here, S over here. Does it make sense? You already knew this, I guess, right? So what happens when you break this magnet into two? Like you get N and S, right? If you break it from here, what do you get?
N and S again. No, they are separately magnets again.
Yes.
N, S, N.
Very good. And this picture that I've drawn over here explains it, right? This one. Why this is happening? Because when you break it in apart, it's still composed of N and S, tiny pieces of N and S. So, let's talk about magnetic poles versus electric charge. Okay? Magnetic poles versus electric charge. So we do have, and we have observed isolated electric monopole. Right? An electron is a good example. You could have an electron and a positron. This is just an isolated plus by itself, isolated minus by itself. Isolated minus and isolated plus by itself, right? That's what we call monopole. When it comes to magnetism, they always come in pairs. As far as we have observed, no isolated magnetic monopole was observed, and this part is important, so far. It's just an experimental observation, and we don't know why, because theory points at their existence. Theory tells us that symmetries actually allow their existence. Symmetries almost want their existence. Do you see my point? But they just don't exist. They haven't been observed so far. Okay? Do you have any comments, questions at this point? No, right? So, for example, theory pointed at antimatter, right? And we observed antimatter. Theory points at magnetic monopoles. We haven't observed them yet. Yeah, sure. Let's now talk about magnetic field. So we show magnetic field usually with this letter B, and it's a vector and it has units of Tesla. Okay? Let me talk about magnetic field lines as well. So let's say you have an N and S like this. Just like in the case of electric field, you have magnetic field lines going from N to S. Okay? And Probably I'm not doing a very good job drawing them properly, but you can look at their images in your books or in the internet. Oops. It's the same story again. The closer they are, the stronger they are. So the magnetic field very close to a magnet is very strong, and it decays down by 1/r². Okay? So far so good? Still, interaction with magnetic field is a bit weird. Okay, it's harder to explain magnetic interactions compared to electric interactions. Let me tell you why. So let's talk about magnetic force on a moving charge. Let's say I have a magnetic field. It was created by magnets. It's a uniform magnetic field, more or less uniform. And I have an electron sitting here. What happens to it? Nothing. Why?
Because it is not moving.
It is not moving. Okay? When it is not moving, there is no force on the electron. Okay? What was the force when it was electric field? EQ, right? And the force would be in the opposite direction of the electric field. The good thing is that things are aligned in electric field, but things are not aligned in magnetic field. For example, what is the force if the electron is moving this way?
Zero.
Still zero, believe it or not, because that's the weird part. Magnetic force involves a cross product, something that you almost never encounter in real life, not in real life, in the macroscopic life, except when you, for example, ride a bicycle, sorry. If it's electric, do we say draw? Anyways. Do you understand? Why I'm talking about the bicycle?
Because you're applying force that way and you're going
Yes, yes, yes. So there is this angular momentum involved, and torque and angular momentum, they act in perpendicular directions. So that's the only place where you have to a bit trick your mind, okay, or train your mind to cross product, okay. But otherwise, it's always I push it this way, it goes that way. It's never it goes this way, I push it this way, and it goes that way. That never happens. But here it is happening. So let me just remind you what cross product was, okay, and how I approach it.
So maybe carrying it back, like we are applying force that way and it goes as we walking, it goes that way.
No. No. There we have no problem. Gravity is this way, bag wants to go that way. We are pushing ourselves forward. Everything is aligned with the forces, and you can explain it. But if you have like a wheel, it's rotating like this, you want to do this, something weird happens, right? It goes like this and stuff like that. Good. So cross product. Let's remember cross product. If I'm telling you that I have two vectors like this, what is the magnitude of their cross product? First tell me the magnitude. Do you remember the magnitude?
Must be sine theta, right?
Yes, and it corresponds to this area.
Yes.
this area corresponds to the magnitude of the cross product. Do you agree with this? So when they are aligned, the magnitude is 0. When they are aligned, the magnitude is 0 because their area is 0. Look, if I have a vector like this and a vector like this, their area is 0. Do you see it? And when they are perpendicular, their area is basically multiplication of their lengths. And otherwise, you correct it with sine theta, right? Magnitude is fine. What about the direction? So the direction depends whether you are crossing A to B, A cross B, or B cross A. They are not equal to each other, right? That's another weird thing that doesn't happen in daily life. Like 3 times 4 is equal to 4 times 3. But here, A cross B is negative B cross A, right? So there are many ways to determine the direction. I like to use the following. Brace yourself for a very bad drawing. Okay. It's a right hand, right? Okay. I have to show it like this so that it's the same thing. Is it the right hand? Yes, it is the right hand. Now, the way that I think about it is the following. You put first vector at the beginning and the second vector, you make your fingers, 4 fingers, go from the first vector to the second vector. Okay? Like, for example, okay. A cross B, right? 4 fingers going from first vector to the second vector, and my thumb points in, right? That's the direction of C, which is A cross B. Okay? How about B cross A? I put the first vector first, second vector second, go from B cross A. Where does my thumb point? Out, right? So D is B cross A. D is the direction of B cross A. And you see A cross B is opposite to B cross A. Okay? So you go this way and your thumb will point at V1 cross V2. All right? So far so good? So if C is equal to A cross B, then the magnitude of C is magnitude of A times magnitude of B times sine theta. Very, very good. Now comes our law of interaction between magnetic field and moving charge. Ready? F is equal to the charge of the particle times V, the velocity vector, times cross product, the magnetic field vector. Okay? This is the way it is. So far, any questions? You already know this, right? So if I have a magnetic field like this, and I have a particle that is going this way, which way is the direction of the force? Of course, I have to tell you what the particle is. Let's say it's a positron. Okay, let's say it's a positively charged object, Q. Okay, which way is the force? Out of the page. Very good. I start from V, go to B, out of the page. And what is the magnitude? Q times velocity times magnetic field times sine theta. Out of the page. And we show out of the page like this. And we show it's like arrow pointing at you. Okay? Into the page, it's like seeing the arrow from behind. It has an X in it. Okay? Any questions at this point? Comments? No? Yeah. So let's talk about motion of charges in magnetic fields. I'm not following the order in my notes, and I'm a bit happy with it. Okay. I have a magnetic field. Let's say magnetic field is pointing in like this. And I throw an electron into this field. What happens next? So you are pointing up, meaning that the force is up, right? Let's see. So this is V. This is an electron having a negative charge, right? Then it's down, right? So V, which way is V cross B? Just tell me which way is V cross B? Upwards, right? V cross B is upwards. This is the direction of V cross B. But the force is minus E times V cross B, right? So that's why the force is down. Do you understand this? Okay, the force is down. So what happens after a moment? Let me just draw it here. It enters with V. The electron enters with V, and after a tiny bit of time, since it's pushing down, it must go in this direction, right? Somehow it must go this way. So it's a bit in that direction. Which way is the force now? Is F perpendicular? Yes, it is perpendicular.
So it's inwards.
No, F is down. B is in. B is pointing in. Okay, V is like this. So V cross B is up, but F is minus E times V cross B, so F is down, right? So which way? Here the force was in this direction. Here the force is still perpendicular, so it will still bend it. It will still continue bending it, right? Which way it will go? It will go this way. It will still keep bending it. Which way will it go? It will go this way, etc. Right? Will this force be doing any work? No. Why not?
Because it's perpendicular.
Because it's perpendicular, right? So the particle has kinetic energy when it enters. It's mv squared over 2. And there is no work being done on the particle. So it will remain, it will preserve its kinetic energy. Although it's changing its direction, since it's preserving its kinetic energy, the velocity will be constant. To speak it in simpler terms, since there is no force and hence no acceleration in the direction of velocity, the velocity will not change. Sorry, that was totally wrong. The speed will not change, the velocity will change the direction. Do you see?
Hocam,
Yes.
V times V.
What is?
V times V, we said, what is it?
It's just, we mentioned it for the direction.
It's
V
not-
cross B is F over E.
But why F is minus E? Like, why it's down? I don't understand.
Because it's an electron. An electron has negative charge.
If it was proton,
It would go up.
Okay.
So that's a typical particle physics experiment. You know, if a photon has enough energy, okay, it will suddenly disappear and reappear as an electron and positron pair, okay? And they would have still some velocities, okay? And what will happen is that if you apply a magnetic field, I drew them. There's no physics here to explain that they will be on top or bottom. I just switched them for practical purposes. So we already have seen that this will go this way, right? The positron would go that way. And you will see that it's just simply known, I will come, it's simply known that they would lose energy and they would spiral down and disappear. It's a typical particle physics experiment that you would see. Yes. Okay. Any questions? So what did we learn from this? We have learned that if we ignore this this fact that accelerating bodies lose energy, so going in circles as a charge is you should lose energy and you should spiral down, but we are ignoring this in physics 102. So as a result, the particle just goes round and round in circles. Okay? So let me just restate what I have just told you. Let's say you have magnetic field and you enter this magnetic field, let's say as a positive charge, Q. Which way is the force? Up, right? Very good. So you will go around in circles. Let me just take this over here. You will move like this. And let's figure out some stuff about this motion. How its radius and velocities are related. So let's say this is r, let's say this is velocity v. So you have a force that has a magnitude of qvb. What happened to sine theta?
Sine 90.
Sine 90 degrees is 1, right? Do you agree? They are perpendicular. So you have a force of qvb, and since it's doing rotational motion here, circular motion, what is the acceleration? There is an acceleration there. What is that acceleration?
Mass
Squared
times.
over R.
V squared over R. Everybody agrees with this?
So it's the same as
Hmm?
101. Like
It's like 101, yes. Why not?
I know it's because it's so small. Maybe
Okay, no. What we have taught you in 101 still applies, of course. So F equals to M times A, and A is V squared over R. So this V takes up this V, and you get this relationship between all of these different stuff. So for example, Q, B, R is equal to MV. You can write down a bunch of relationships here. R is MV over QB, for example. So your radius depends on your initial momentum and magnetic field and your charge. All right, good. Any questions at this point? Let me solve for you an example. I have a magnetic field pointing in this direction. Anyways. Okay, this one looks ugly. So I have a magnetic field pointing in this direction. When I plot just one line, please understand that it's all over the place, right? I have this magnetic field everywhere, uniform. Then I throw a particle with an angle theta. All right? Can you describe the motion of this particle? What will happen?
maybe it will draw a circle. Eventually.
In which direction? Towards the page.
Because the force is perpendicular to the page.
Yes, very good. So V cross B, if it's a positive charge, let's say this is plus Q, and V cross B points into the page, right? So here we actually need to break this down into pieces, into projections. Like you have Vy part and Vx part. Is Vx part affected by the magnetic field? No, right? It's aligned with magnetic field, so it will not feel a force because of that. So the force that we have here is due to Vy, right? And the force is pushing in. So it will circle inwards, right? But will also continue moving to the right. So it will go like this. Okay, it will spiral. Let me draw it like this. Very hard to draw. Yes. So I've started over here, let's say, and this is my cylinder. So it will go like this. No. Did I draw it well? Yes, do you understand it? So it goes like this. Yes.
How we found the direction of F?
How did we find the direction of F? So V cross B, you start your four fingers at the first vector v, go towards B, points in, right? So it starts like this. The force points in this direction, so that force keeps rotating it. But it also had the horizontal velocity, which doesn't change, right? It doesn't change magnitude or direction.
And force is the in change direction with v times v, right? Because
Say
it's
it
a
again, please.
Plus, because it's a plus q, v times v
Yes,
cross
yes.
v
V
is
cross B is the same
same
direction as QV cross B. Yes. Very good. So if we look from here, we will see a circular motion going like this, right? And if we look from here, okay, we will see going up and down like this, but let's not look from there at all. It's a helix, right? It's a helix or helix? Helix. Helix. So let's find this distance. Can you find this distance? Yes? Tell me.
Since you circled one time, you know you can calculate the period. And
Yes.
period times Vx.
Very good. Very good. So x is equal to Vx times the period, right? And to find the period is the time it takes for it to come back, circle and come back. So we need 2 pi r, where r is this radius, right? Divided by Vy. Do you agree? Everybody agrees? So what is the relationship between r and Vy? Let me tell you this way. Q Vy times B must be equal to nVy squared over r. This goes away, that goes away. R over Vy is what? QB, m over QB, right? This means that the period is 2 pi times m over QB, and the x is going to be 2 pi m over q times b times Vx, which is, let me call it V0 times cosine theta. Let me drop this V naught because we didn't start with V naught, or let me put it here back and put it also here. So this is our result. Typical exam question, right? You have a couple of different things going on and you describe this distance. Yes?
But this isn't the exact value because the x is going to be larger and larger by time.
Why larger and larger?
Because we lose energy and
Yeah, forget about losing energy, okay, please. But why do you think we lose energy? Can you explain it back to me?
because it's moving and some things have to happen.
It's different from dissipation. It's different from friction.
But there's
You know, it's not slowing down because there are dust particles and it's hitting them. That's not what the reason for this one. That's not why this is happening. Okay? Why this is happening is that while it's moving, you have electric field creating magnetic field creating electric field. Basically, it radiates light. So it loses energy because of an advanced thing going on. Like accelerating bodies lose energy because they radiate electromagnetic waves, that kind of stuff. But we ignore that effect, okay? If we ignore that effect, then it's basically a combination of circling and moving it on a straight line. All right?
But if we don't ignore that, T is still stay constant because it does not depend anything.
Yes, that's a very good point. T does not depend on what? On velocity. So the period does not depend on velocity. That's a very good observation.
X is changing because Vx is changing, but T is.
Say it again, please.
X is changing because Vx is changing.
Yes, exactly, exactly.
Hocam why is that T doesn't depend on velocity? Isn't it depending on the...
So let me talk about it a bit further. Something called cyclotron frequency. Okay?
Omega.
Yes. So I have a charge plus Q moving up, right? If V cross B, yes. If magnetic field is this way, then it will be moving up. Will be circling like this. Do you agree? So let's find omega, which is 2 pi times the frequency. Do you remember this stuff? Which other way I can define it? 2 pi over t also. So we have already found t, right? 2 pi times m over qb. So let's plug it in. Omega is qb over m. Is this correct? So this is something called synchrotron frequency. Did I write this correctly? Can you please check? Can you please check? You have magical devices to check it. No one is. Okay. Why this is important? Because as we discussed, it doesn't depend on radius, right? So you can use it. You can use it to accelerate particles. Good? How can you use it? For example, let's say you have magnetic field here and magnetic field here, but in between you are applying electric field that is switching back and forth with synchrotron frequency. Okay? So when a particle starts here, it is being accelerated and it enters to this field. Okay? Which way is the force? It pushes it to the left, right? Yes? So, no magnetic field here. No magnetic field here. There is a magnetic field here. There is a magnetic field here. Okay. And magnetic field here. No magnetic field in between. Electric field accelerates the particle and the particle goes like this. Okay? But then in the meantime, since we are giving it just the right amount of frequency, when it comes back, the electric field is pushing it in this direction. Did you follow this? I should really start this particle from the center, because otherwise I will run out of space. So I have accelerated it, it entered here, went like this, then just at the right moment the electric field is pointing in the opposite direction, so it gets accelerated over here, got accelerated over here, gets accelerated again, Now it has more velocity, so it goes here, gets even more accelerated because the electric field was switched just in the right moment. Are you following? Yes or no? So it will get more and more accelerated, and you can use, so this is your beam, you are creating a beam, you can use any part of that beam at any point you want. Maybe there is an exit here where there is no magnetic field applied, so you can harvest your accelerated particles from there. But what did we use here? We used the fact that this cyclotron frequency does not depend on the velocity of the particle. It only depends on the magnetic field, the mass, and the charge of the particle. You can control the magnetic field, right? And charge and mass of the particle will not change. So it's very nice. Okay. Should we have an early break?